Okay, so we're just going to solve this problem here, and I'm just going to sort of talk through the solution real quick. Okay, so basically you're given an integer x, and you're trying to find out if you can make x by summing some number of 1, 1, 1, 1, 1, 1, 1, so on and so forth, right? So you essentially have an infinite number of these the sequence is infinitely big, and then you're trying to find out, if your number is a linear combination of any of these numbers. So I think, okay, so you look at the limit here, and we see that the limit is 10 to the 9, right? So that gives us sort of a lot of numbers to deal with, because you have anywhere from like 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on and so forth. Right, so I think the intuition behind saying, okay, well, maybe let's not consider all of them. Let's see if we can simplify the problem a little bit, right? So I think we can do that by, you sort of notice that the numbers that you're allowed to work with, right? So I'm just going to write them out real quickly for clarity. Numbers that you're actually allowed to work with are 11, 111, 1111, 11111, 11111, and then so on and so forth. But you notice that in sort of every one of these cases, you can sort of split this up into, you can divide this into two ones and 3 ones, right? So look at these two, and then you say, okay, can I divide all of these numbers into, sections of 2 and 3? And so the answer is going to be yes, right? So here's 3, there's 2, or you could have done 2 and 3. There's 3 and 3, and so on and so forth. Right, so more formally, this is really saying, assume that you weren't bounded by 10 to the 9. More formally, this is saying, okay, well, can any sequence of 1s be represented as a linear combination of 1, 1, and 1, 1, 1? And so when you think about it, that has to be true if you can perform this split, right? If you can perform that split. Because all the split is doing is it's just shifting over to the left, which is just multiplying by some power of 10. Right, so if you can perform the split, then it has to be true. And so let's consider that this is arbitrarily long. Let's say it's n long. So you're essentially trying to solve 2x plus 3y equals n, right? So does this have a solution? And you're interested in saying, okay, well, given 2x and 3y, what is the solution space of n, right? So what can n be? And because 2 and 3 are coprime, you know that n can be anything in the integers. Okay, cool. So I think that's sort of the most important, step to take, because then the rest is, you can just sort of compute, right? So I think the crux of the problem lies here, and you sort of say, okay, well, now that, let's just make a divide. Now that I know that I can represent any sequence of 1s, which is these two, this problem really just boils down to, let's say if I have the number x, if I can do 11a plus 111b equals x, right? So can I solve this? And so you notice this sort of just boils down into solving a linear Diophantine equation, right? And so you can do that with the extended Euclidean algorithm. Or this video, or in the video by HealthyUG, which I'll put in the description, he sort of says you can imagine to simplify this and not have to use the extended Euclidean algorithm, you can sort of just take the modulo by 111, right? So, you can say 11a, so let me change colors. You can say 11a plus 111b mod 111 is congruent to x mod 111. Right, and so this modulo, so we can sort of distribute this in some sense, right? So we have 11a mod 111 plus, so notice that this goes away because this is divisible by 111 because there's that factor of 111. So that just goes away, plus 0 is congruent to x mod 111, right? And now we have to find a, right? And so if we're able to find a, because we're given x, right? So if we're able to find a, then we can sort of solve, then we're sort of done. Then we can solve this problem. So how do we find A? We say A mod 111 is going to equal 11 inverse, right? The modular inverse times X mod 111, right? Modular inverse of X times 111. Okay, so then this just comes down to solving, just computing the modular inverse of 11 in the world of mod 111, and that we can do pretty easily just because this number is not very big, right? So that's pretty small, which means to find the actual modular inverse, we can just say for I in like 1 to 111, or so I guess it would be that, right? If 111 mod I equals 1, then I is your modular inverse, right? And so performing this will, from this we can extract this quantity A here, and then if we get A, then we can that allows us to also get B in the same way. So that's sort of the solution to the problem. And then I'll in the next video in the next section we'll look at the code for it.